Hello dear students. So here we have a small animation for you based on which we will look at today's theory topic. So here we have a cannonball system where we can fire a cannon, and here are various parameters that we can see. So first let us just fire it and let's see what happens. So this is the cannonball that is fired, and we can see that there is a particular path that has been traced. Now I can use this finder to just, let's say, place it here and look at what values we get. Okay, so at this point the time is 2.4 seconds, range is 7.5 meters and height is 14.29 meters. And it has an initial speed of 18 meters per second. Okay, so what are we actually looking at here? So in this video we are going to go ahead and look at projectile motion. So before we get into the theory of it or look into the mathematical part of it, let's have some fun. So I'll put this back and let us see what happens when we increase our velocity slightly. So let's say I have increased it by, it was 18, by 6 units. Let us increase it. And now let us fire the cannonball. Whoa. Well, does it come back? Yes, it does. But you can see that it has gone out of the range. So yeah. So we have minimized it. Whoa. So you can see that just by changing the initial speed, the distance that it has moved is quite large. Now there are a couple of things here. We've taken gravity to be 9.8 meter per second. The diameter of this cannonball is there. The mass is also given as 17.6 kg. So we will not change the mass, diameter and the acceleration due to gravity. But rather what we will do now is, we will just change this angle. So I'll zoom in a little bit. Well, it's showing 80 degrees. Let us bring it down to, let's say, 50 degrees. And then let us fire our cannon. Now the idea of this activity here is so that we hit this target which is at a distance of 15 meters. So we can figure out at what angle, if we launch the ball from the cannon, we can get it to be at 15 meters. Now we did it for two different speeds. One for 18 meter per second and the other for 24 meter per second. And we found that the 24 meter per second fell further away from our 15 meter mark compared to the, let's say, the initial 18 meter per second. Now let us fire this. So 24 meter per second at an angle of 50 degrees. Well, it's gone way out of range. What we'll do is we'll reduce the initial speed. Let's say we make it 18. And then again let us fire. Okay, so 50 degrees doesn't cut it. Maybe we will take it a little back. We'll make it 65 degrees. Well, close. So that means we'll take it somewhere close to 80. We'll make it 75. And we'll fire again. And okay, that means a little more to find the bullseye. So 75, 78, let us try. No, so it is in between 75 and 78. Let us look at 76 degrees. That has hit close to the bullseye. What happens if we move to 77 degrees? Okay, that is close to the bullseye. Now, since we cannot measure an angle in between, we will not be able to get it. But if you see here, each of the paths that has followed, it has followed a certain curve type path that is there, which in mathematics we call as a parabola. So if we take the finder and let's have a look at this. So it is at a height of 8.72, time is 3 seconds, 8.52, time is 3 seconds, 8.3, time is 3 seconds, and 8.06, time is 3 seconds. So if you see in all four cases here, which hit close to the bullseye, the time is 3 seconds, but there's something called as range. The height is varying. So it was 0.5 to 8.7. Now let us look at what is the distance. If you see, mean, it's fixed. Practically this is 15 meters that it is given. So we don't need to actually measure it, but yeah, fine. So what is happening here? We have launched a cannon. Let's just refresh this. Again, it's gone back to its original. And let us see if we launch a couple of different items here and see what we get. So we finished with a cannonball, but we will just fire it again just for the sake of it. Yes, so this is our cannonball. So this is one path. Cannonball mass is 17.6 kilograms. Now let's take a tank shell, 18 kilograms. The diameter we can keep the same as that of cannonball. Diameter not going to change, only mass we will change. Acceleration due to gravity is 9.8. And let's fire. Okay, that too has traced the same path. Let's look at a golf ball. It's very small, 0.05 kilograms. And fire. Wonderful, it has traced the same path again. Let's take the baseball. Okay, so we can see it coming down, and yes, baseball also has traversed the same path. Let's look at a football. It's the same path. The pumpkin. And yeah, it is smashed. Now let's, a little bit of circus. Let's see if we can launch a human. And let's see what path the human takes. Wow, the same path. For fun, let's look at a piano. It's broken. And let's look at a car. So in all of this, what is the common thing that we have seen? The common thing is, see, we've kept the angle at 80 degrees, speed is 18 meters per second. We have varied the items that we have taken. So the mass varied, the diameter varied. We have kept the acceleration due to gravity a constant. The initial speed is a constant. It is tracing the same path, which again in mathematics we call it as a parabolic path, or the path of the projectile. Because if you see here, this cannon was launching everyone as a projectile. It's like it's being projected outwards. So let's say at this point, if it would break apart, then what will happen? One will go in a slightly different direction. So we can do that. Let's say we'll increase it by 2 and we'll launch the car again. You can see that it is getting projected. So that means there is going to be a change in the direction. So there are a lot of factors, that is the angle, the initial velocity that is there, initial speed that is there, and the items that we are using. But one thing that we have not kept in mind, or one thing that we don't take when we, let's say, go ahead and derive the expressions for this projectile motion is air resistance. So air resistance is not taken into consideration. So we are looking at an ideal case where we are telling that this is how it is going to change. This is one of the most important motions in two-dimensional studies of physical motions. So let us look at the definition and then we'll move on. So according to a definition, when a particle is thrown obliquely near the Earth's surface, it moves along a curved path under constant acceleration that is directed towards the center of the Earth. We assume that the particle remains close to the surface of the Earth. The path of such a particle is called a projectile and the motion is called projectile motion. So now for instance, let us say when you are playing catch, cricket, football, any of the games, maybe even a javelin throw or a shot put throw that is there, it is always seen that there is a curved path that is taken when it moves from one point to another. For instance, let's say a player has hit a 6. So in the cricket, when the person hits a 6, we know that it has to reach the boundary. And the boundary is nowhere close to the batsman. So as the ball has to travel, it travels basically in the curved path. Even if we take, let's say, planes. When we travel using aeroplanes, jet, any of these, they travel in this curved path that is there. And this path is called a projectile. Now motion along this path is called a projectile motion for one particular reason, that this path, if you see, at any point if I draw a tangent. Now when I tell a tangent, it is nothing but a line that touches the curved path or the arc at only one given point. Now this would basically be projected outwards, that is away from the path. That is why the name projectile has come into the picture. For instance, if you would have watched in certain movies, the shelling that is there. So there is a tank and somebody is shooting out of it. Now the path that is taken is a projectile motion. And so on and so forth. So in 2 dimension, projectile motion is one of the most important motions. The understanding of this motion will basically help in trying to understand what will be the maximum distance that we have covered using this particular motion. So let us go ahead and look at the mathematical part of this and then try and understand using a few numericals. So for the projectile motion, first what we will do is we will take 2 axes. One is x, one is y, and we have this motion, the curve that is there, which is supposed to be a projectile motion. Now what we will do is we can draw tangents at every instant. So let me draw a tangent here. So this will be the direction. Similarly, if I draw a tangent here, this is going to be the direction. This is one more. This is one more. And this is one more. So if you see, I have drawn 5 different tangents at 5 different points. Now the reason why I have done this is I have basically tried to plot my velocity here. So what we can do is, instead of giving this convention x and y, we can understand this in terms of vectors, saying that I have plotted a velocity vector in a 2-dimensional plane. So when I try and resolve, I can actually find out what are the components. So for the first one, if I see, the component is going to be ux and uy, because this is initial velocity. Now as it is moving on top, I can have another component that I draw here. So this is again ux, this is uy. Now if you look at the third one, it is no longer moving up. So it does not have a vertical component of velocity, rather it has only a horizontal component of velocity, which I'll simply write it as ux, because the body is moving forward. Now on the other leg of the journey, we have got, it's still moving in the forward direction. So I've got ux, but it is descending downwards. So I'm going to have uy in the opposite direction, that is downwards. Just to differentiate between the first and the second, we can put this as minus, which depicts that it is moving downwards. Similarly, for the last tangent that I have drawn, I have got ux and uy, which is moving downwards. So here we can see that it is moving with the initial velocity, and since it is coming to rest finally, or if let's say it is going downwards, what we will do is, instead of ux, we will just change this to uy, or in terms of final velocity we can write. So this last part of it, what I will do, I will replace it by vx and vy. Even if I leave it as u, it doesn't matter, because in the derivation towards the end we can replace it. Now let us begin. So if I tell u is my initial velocity, what I have done here is I have resolved it into its components. Ux and uy as the components. That means I can write the u vector as ux I cap plus uy j cap, where ux and uy are the magnitudes of velocity along the x and the y axis. So accordingly, what we can do is, right now we know that this projectile would be at any given angle theta. So when we are resolving, we can write ux is equal to u cos theta. Projection along x-axis is generally in terms of cos theta, and uy as u sin theta. So we have resolved the components. So you see, we can write this as u cos theta plus u sin theta. So finally, if I have to find the modulus of u, it is nothing but root of ux square plus uy square, which is going to be root of u square of sine square theta plus cos square theta, which I'm going to get it as u. Because we know the relation sine square theta plus cos square theta is equal to 1. So using certain mathematical relations and trigonometric functions, we will try and find out what is the range of this particular, let's say, projectile. Range, when I tell how much is the maximum distance it can travel. Also, we will estimate what is the maximum height it can travel to, and what is the time taken to obtain both the maximum height as well as the range. So in order to do this, let us begin by first trying to understand what would be the distance that is covered. So for this, what we can do is, we will use the simple idea that I have got x is equal to ux into t. The distance traveled along x is the velocity along x into the time. What is velocity along x? Is nothing but u cos theta times t. Now what I will do is, I will do a small rearrangement where I will write t is equal to x by u cos theta. This I will take it as my first equation. So this is the distance traveled along x-axis. If I am going to look at the distance traveled along y-axis, then we will use the relation s is equal to ut plus half at square. Now since it is moving upwards, we are taking the first leg of the journey. So since it is moving upwards and against the pull of Earth's gravity, this equation can be written as s is equal to uyt minus half gt square. Now s is nothing but displacement along y-axis. So for simplicity, we will write it in terms of y. So y is equal to uy, we know in terms of u and cos theta, or u and sin theta here. Since it is along the y-axis, u sin theta into t minus half gt square. So what we can do is, we can rewrite this so that, see, the thing is, it is sine theta, sine of the angle, not sine theta into t. So what we will do is, we will simply make small change. Y is equal to ut of sine theta minus half gt square. Now this is equation 2. So I will go ahead and substitute equation 1 in equation 2. Now the reason why I had initially found out time from the x-axis is, I am going to substitute it here. So you see, I get y is equal to u sine of theta into, what was t? If you see previous first equation is x by u cos theta. X by u cos theta minus half g x by u cos theta the whole square. Now here, if you see, u can get cancelled and sin theta by cos theta is tan theta. So this is equal to x tan of the angle theta minus half g x square by u square cos square theta. Now this is equal to, now if I rewrite this expression, or if I can write it again in the next page, I have got y is equal to, I had x tan of theta minus gx square by 2u square cos square theta. Now this is the equation of the projectile. So if you see, what have I effectively done? I have written y is equal to f of x. That means y as a function of x, because we are plotting a graph of x versus y. So for different values of x, we can calculate the value of y, and governed by this expression, we get this projectile motion. So this is the equation of the projectile. Now from here we will go ahead and calculate the remaining terms that are there. So now we have to calculate maximum height. So what is maximum height? If you look at this, the highest point up to which our projectile can travel along the y-axis. So if you look at it, we know that the initial velocity was nothing but uy, which I can write it as u cos theta, the initial velocity along the y-axis. Now the final velocity along the y-axis is 0. The reason for this is, at the maximum height, it can no longer go up. That means it has reached the maximum height. After this, what happens? You can see that it comes down. That is the only path it has left. It can go up maximum height and then it can come down. Now, if we are going to look at it, maximum height, I can write it as h. We can solve this using the third equation of motion, which is v square is equal to u square plus 2as. So v will be the final velocity, u is the initial velocity. Now since the motion is along y-axis, the acceleration is replaced by acceleration due to gravity. So we can have it like this. V square is equal to u square minus 2gs, minus negative sign because it is moving upwards. That is against gravity or against the pull of gravity. So if I go ahead and substitute, so we will make small changes. We will write this as vy square is equal to uy square minus 2g, height becomes h. So vy square is 0, whereas uy square was u sine of theta the whole square minus 2g capital H. That would imply 2gh is equal to u square sine square of theta, or h is equal to u square by 2g of sine square theta. So this is the expression for maximum height that the projectile can, let's say, obtain when it is moving in this particular projectile motion that is there. So let us look at this expression. Now I have got h is equal to u square by 2g into sine square of theta. So if I look at this, I can say that my height is proportional to the initial velocity and also directly proportional to the angle. Though it is sine square, we can just take it that it depends on the angle. Now, here if you see, g is a constant, so 2g is going to be a constant. So the variation of height is only because of initial velocity and theta. Now, if I take theta is equal to 90 degrees, that means I am projecting it straight upwards. We'll have to find out what is the maximum height obtained. So in that case, h will be equal to u square by 2g sine of 90 degree the whole square. Sine 90, as it is known in terms of trigonometry, is equal to 1. So therefore the maximum height will be nothing but u square by 2g. Now this is one useful relation when we are looking at competitive exams. So now let us look at the time taken by the projectile. Now we know that the path taken is parabolic. Now when we talk about time taken, there are a couple of things that we can understand. Now the first thing that we can look at is the time taken for ascent. That means if I'm going to take this as my projectile, how much time it takes to ascend to the highest point. Now for this, if we see, at the highest point, the final velocity is 0. This is along the y-axis. And the initial velocity is u sine theta. So what we can do is, we can find the time of ascent, that is, for it to move up to the highest point using the first equation of motion, which is v minus u is equal to at, or t I can find as v minus u by a. Now we'll have to be a little careful here as to what we are going to substitute. Now Vy and Uy we know. Now since the object is moving up along the y-axis, that is away from the Earth's surface, the acceleration that we are going to talk about will be acceleration due to gravity. So it is going to be V minus U by minus G. Minus because it is moving away from the Earth's surface. So if I substitute, the total time taken for ascent will be equal to Vy is 0, U is going to be minus U sine of theta divided by minus G, which I get as U sine of theta by G. So now if we see here, time of ascent is U sine of theta by G. Now here also the time is dependent on initial velocity and the angle, because the angle will decide how high the projectile can go, and based on the initial velocity how high it goes also we have seen. Now the idea is to find the time to reach this particular height. The next thing that we can go ahead and find is the total time. So if we see in the projectile motion, we have told that this is how it is going to go and come back. And we have found out what is the time taken for it to reach the maximum height. Now the understanding is, if let's say we throw up something straight, let's say you throwing up a ball, and let's say it takes 1 second to reach the highest point, then it is going to come down in the next 1 second. It is not going to take more than 1 second or less than 1 second, because the distance it has traveled is going to be the same. So the total time, what happens, we can take it as twice the time. So keeping that idea in mind, the total time t, I can write it as 2 times time of ascent. That means I am telling time of ascent is equal to the time of descent. How much time it takes to go up, the same time it takes to come down. Now this is true for a projectile motion because of the governing equation that we have in terms of y that we already derived. That is the path, equation of the path that is there, or equation of the projectile motion. So from here, since I know both are same, I can write capital T is equal to 2 times. Now what is time of ascent? Previously we derived it as U sine theta by G. So this is 2 times U sine theta by G. So this is the total time that has taken for the projectile to start from, let's say, point A and reach point B. Now the next thing that we have to look at is the horizontal range. So when I talk about horizontal range, I am basically talking about this distance. If I take this as A and this point as B, what is this distance that has been traveled? And this we give it the symbol R. So now if I have to look at horizontal range, I will only look at the velocity along x-axis and the time taken to cover the velocity. So range, capital R, is equal to horizontal velocity into total time. Now this total time is of the flight. That is, since the projectile is moving away from the Earth, that is in the atmosphere, we call it as flight. Now horizontal velocity is nothing but ux into total time of flight is capital T. So we can go ahead and substitute the values. So capital R is, ux is nothing but u sine theta. Now the total time that is taken, we saw it as 2u sine theta by G. So 2u sine theta by G, or we can write it as 2u square sine square theta by g. So this is the range that is there. So now the horizontal range r is equal to ux times capital T. Now ux is u cos theta into capital T, that is the time is, we found it to be 2u sine theta by g. Now here we have got u square 2 sine theta cos theta by g, or I can write this as u square by g into sine 2 theta. So now this is a half angle or multiple angle formula that is there in math, where I can write sine 2 theta is equal to 2 times of sine theta into cos theta. Now this is a standard formula that is there that we are using here. So I get u square by g sine 2 theta as the horizontal range that is there. Now here also if we see, r is proportional to the initial velocity and proportional to theta. Since we have got the expression as, let's say, r is equal to u square by g sine 2 theta. Now if I take theta is equal to 45 degrees as my angle, r will be nothing but u square by g into sine 2 times 45 is 90 degrees. So that is going to be u square by g. So the maximum range that can be, let's say, covered for a given initial velocity is when angle theta is 45 degrees, because sine becomes maximum. Sine 90 is equal to 1, which is the maximum value of the function sine. So that means the range that it is going to cover will be the highest. So we can just quickly have a look. So I have got my equation of projectile as y is equal to x and theta minus g x square by 2u square cos square theta. Then we found the maximum height to be u square sine square theta by 2g. We went ahead and found the time for the total time for travel. So time for ascent we found, but we would like the total time for travel. So capital T 2 times u sine theta by g. We found the range to be nothing but u square sine of 2 theta by g. So now if we see, in all of this we've got u sine theta and g as common. So we can try and find what is the relation between the height, time and range. So what I can do is I can simply write 2 times h is equal to u square sine square theta by g. Or let's have a look at it like this. So if I write h is equal to u square sine square theta by 2g, and I have got the total time of flight to be 2u sine theta by g. So rearrange the second part. I will have gt by 2 is equal to u sine theta, or gt by 2 the whole square as u square sine square theta. So let me substitute that here. So I will get h is equal to 1 by 2g into g square t square by 4, which is 1 by 8 g t square. So we can see that the relation between height and the total time of flight is this. 1/8 gt square is equal to h. The thing is, between, let's say, time and range or height and range, we cannot do the same. We will get a slightly complex equation if we try equating u square by g. The reason is, this is sine 2 theta. So we can try looking at, let's say, height and range. What is the relation in between them? So if this is the relation that I have, I can write u square by g, which I have in height, as r by sine of 2 theta. So we can substitute that here. H is equal to sine square theta by 2 times. Now u square by g is r by sine of 2 theta. So we can write this as r by 2 into sine square theta by sine 2 theta, we know it is 2 sine theta cos theta. So one of the signs can get cancelled, and I will get this as r by 2 times, or rather sine theta by 2 cos theta. So h, I can write it as r by 4 times tan of the angle. So this is the relation between height and range. Well, as we have finished the derivation now, we can again launch this cannon and we can see a couple of things that we have. So first, let us launch it. So we have a cannonball. Yes, that launches and it reaches here. Good. Now, let us look at the components that are there. So this was the total diagram that was there, where the velocity keeps on changing along this blue line that is there, or the projectile path, or the equation of the parabola that we have seen. Now, if you look at the components, again, we have the total components. So which component would we like to look at? Let us look at the velocity components. Now, in the diagram earlier I had shown that we had uy moving upwards and ux along the horizontal. Once it reached the topmost, we would have only ux, and as it came down again, we would have both ux and uy. So what we will do is, first we will watch it in normal motion, and then we will look at it in slow motion. So we will launch it, look at how the velocity vector changes. So let's just look at it in slow motion. You can see that as it is reaching this particular height, the velocity becomes 0, vy becomes 0. As it comes down, again vy increases. So this is in terms of velocity. Now let us look at what happens if you're looking at acceleration. Does the body gets accelerated during projectile motion? So here you can see that the acceleration due to gravity increases. So it's maximum here, and as it is coming down, it's almost a constant, because we are looking at an acceleration due to gravity of 9.8 meter per second square on Earth. Let us look at what happens to the force vectors. So the force of gravity almost remains the same. Maybe there is a slight change, if you can notice. It's not much, but as such the force remains the same, because of which it is being pulled down. Now, if let's say we increase the mass from 5 to 10 kilograms, let us launch it again and see what happens. Well, the force remains a constant. We do not see any variation in that. So we'll put in all our vectors, that is acceleration vector, velocity vector, and the force vectors. Now let us launch it again. So we can see that the velocity vector is changing, whereas the acceleration vector remains the same. The force as such would remain the same. So this is what happens in a real life scenario. So when we are taking all three vectors, we will have to see. But for our derivation, we took only velocity vector because we were mostly concerned with what was the velocity with which we have to launch and with what, let's say, angle we should launch for a maximum range. So we'll do one thing, we'll just reset this. We will change our angle to 45 degrees, where we told that it is going to go the maximum horizontal distance. And let us zoom out. Now let us launch it. So we will just monitor the velocity components here when we launch it. So you can see that the horizontal velocity increases. You don't have to zoom out. So again, let us see it. You can see that the horizontal velocity is quite a lot. The vertical velocity decreases, but the horizontal velocity increases. Now in this case, let's look at acceleration. Along the x-axis there is a change, but along the y-axis there is no change, because the acceleration is due to gravity. So look at it. Yes. Now we have got force dy. So here you see air resistance has been clicked. But in our derivation, we have never seen air resistance. So we have not considered that. So if we remove this and let's say we replot it. So again we will go and we will put this to 45 degrees. We will launch it. We will look at the total number, both the components of all three. So here you can see that, well, there is a change in acceleration along x, but not along y. The force vectors remain the same. 1 minute. That was because drag was introduced. So now you see without drag, it goes to a much larger distance. So the range changes when there is no drag at 45 degrees. Acceleration remains the same. Now when you have drag, it is like a resistive force. So the projectile motion, though it is still following the parabolic path, the maximum height, the time of flight as well as the range is going to change. So instead of 15 meters, now this range would be 33 meters. So in presence of a resistive force, that is air resistance or drag, we get 19.6. So in the derivation, we don't take drag into consideration because compared to the size of the object that we are looking at, the drag is going to be very, very less. So in this question, it is given that an athlete throws a javelin to a maximum distance of 80 meters. How long is it in air and to what height does it rise? So when you look at the question, there are a couple of things that are given. One, the maximum distance. Second, how long is it in air? Third, how high does it rise? Also, they have given neglect height of the athlete. Now, in certain cases, we can have numericals where the height is considered. But here they have told that we can neglect the height of the athlete. So if we are looking at our solution, let us just first draw a diagram. Now every time drawing a diagram basically helps us in understanding what is happening. So I have this as 80 meters, which is our range. So if you can find the maximum height, we know that we can even calculate what is the time that is there, or if we can calculate what is the time, we can try and figure out what is the height. Another thing that is given is G is 9.8 meter per second square. One thing to understand, in the question if they mention G as 10 meter per second square, then only please take it as 10. If they have not mentioned anything, you have to take the standard value, which is 9.8 meter per second square. So total time we need to calculate, also the height. So let us go ahead and see how we can solve this. Now if we have to calculate the total height or the time, we know that sine of the angle comes into the picture. So h, I can take it as u square sine square theta by 2g, and the total time of flight is given 2u sine theta by g. Now we have a fresh problem. We do not know what is the initial velocity. Also theta is unknown. But if you look at the question, we can figure out theta. It says maximum distance. Now the horizontal range that is covered, that is 80 meters, is when the angle at which the projectile is launched is 45 degrees. So at this maximum angle, we get the distance to be 80 meters. So we can use the range expression, that is r is equal to u square sine 2 theta by g is equal to u square sine 2 into 45 by g. Now if you see, r is given as 80, u square by 9.8 into sine 90, and sine 90 is equal to 1. So we can as well write it as 1, or we can leave it out. So here I will get u square, or we can just directly write it as u is equal to square root of 80 times 9.8, which will give us 28 meter per second. So we have our u, we have theta. Now we can proceed to calculate both the height as well as the time. So the height is given by this expression, u square sine square theta by 2g. Now we've calculated it to be 28, so 28 square into sine 45 square by 2 into 9.8, which we can write it as 28 square by 2 into 9.8 into 1 by root 2, sine 45 is 1 by root 2, the whole square. So this will give us a height of 20 meters. Now we found the height. Let's go ahead and calculate what is the time. So the time, total time of light is given by 2u sine theta by g. So it is 2 times 28 times sine 45 by 9.8. So 2 into 28 by 9.8 into 1 by root 2, which gives 4.04 seconds. Here we have a question. A stone is fixed at a distance of 39.2 meters from the foot of a pole 19.6 meter high so that it passes over it. Find the direction and magnitude of velocity of the stone. So first we will go ahead and draw a diagram for it. So here we have, along the x and y axis, we have drawn a two-dimensional graph. The red curve that is there shows the path that is taken by the stone, which is a projectile motion. And as it says, it just passes over this column of height, or this pole of height, 19.6 meters. So right now, if you have a look at what all is given, I can say that I have been given a total height of 19.6 meters, which is exactly halfway through the distance, or halfway of the range. So if I take my given distance x as 39.2 meters, then the range can be taken as 2 times x, which is 2 times 39.2, which gives me 78.4 meters. So this is the range that we have the height. Now, given that we have to calculate the velocity. Now, when we are trying to calculate velocity, we have seen the expressions both for h and r. So let's have a look. The total height is equal to u square sine square theta by 2g, and the range is given as u square sine 2 theta by g. Now let us go ahead and take the ratio of height to the range. So I will get u square sine square theta by 2g whole divided by u square sine 2 theta by g, which we can write it like this: u square sine square theta by 2g times g by u square sine 2 theta. So g and u square gets cancelled. So we will end up getting h by r is equal to, numerator I will have only sine square theta, denominator it is going to be 2 times sine 2 theta. So that is nothing but sine square theta by sine 2 theta can be written as 2 sine theta cos theta. That becomes 2 times 2 sine theta cos theta. One of the sine can get cancelled. So I have h by r is equal to sine theta by 4 cos theta, or 4 times h by r is equivalent to tan theta. So from here I can tell that tan theta is equal to, let us substitute the values, 4 times, the height is given as 19.6 and the range we found 78.4, which will be 4 times 1 by 4. So tan of the angle is equal to 1. That would imply theta is equal to tan inverse of 1. That means we have taken tan to the other side. This is, let's say, literally speaking that we are taking tan to the other side, but mathematically this is an inverse function. So we can calculate what is the angle. Now theta is 45 because for tan 45 the value is 1. So here we have found the value of theta. Now let us go ahead and substitute it in any one of the expressions. Let us take the maximum height expression, which is h is equal to u square sine square theta by 2g. So we need to find u square. So I can just write this as u square is equal to 2gh by sine square theta. Now theta is 45 degree and sine of 45 is equal to 1 by root 2. So sine square 45 will be nothing but 1 by root 2 the whole square, which is equal to 1 by 2. Let us substitute. So I have u square is equal to 2 times 9.8 into 19.6 divided by 1 by 2, which is 2 times 2 into 9.8 into 19.6. So our u square will be equal to 768.32, or u is going to be square root of 768.32, which will give me a value of 27.70 meter per second. So therefore I can tell the magnitude of velocity is 27.70 meter per second with an angle of 45 degrees with respect to the base. So here if I go back, I can tell that this angle is 45 degrees and the initial velocity is 27.7 meter per second. In this question it is given that a projectile is fired at an angle of 30 degrees with respect to the horizontal such that the vertical component of its initial velocity is 80 meter per second. Time of flight is capital T. We need to find what is the magnitude of velocity at a time which is 1/4 the time of flight. So if you see here, what all have they given us? They have given us an angle which is 30 degrees and they have mentioned uy, the vertical component, to be 80 meter per second. So if we go ahead and draw a diagram for this, for our parabolic path. This is how it's going to be. This angle we can take it as 30 degrees, and uy is what is given. Now ux is unknown. So we know that when we take the components, ux is u times cos of theta and uy is u times sine of theta. So what we can do is we will take the ratio of ux by uy, which will be u by u sine theta, which is going to be equal to, we can write it either as 1 by tan theta or we can write it as cot theta. So ux will be nothing but uy times cot theta, which is uy we can take it as 80 into cot 30 degrees, which is 80 times root 3. So this is our ux, meter per second. So we have the x component of velocity. Now if you look at the total time of flight, that we can get it using this expression. 2 times uy by g, which is nothing but 2 into 80 by 9.8, which we will get around 16 seconds. Now the time is 1/4 that of capital T. So 16 by 4, that means for 4 seconds we need to calculate what is the velocity. So we have 2 into 80 by 9.8 is 16.32 seconds. I approximated it to 16, but this is the exact value. So therefore the time that we get is 4.08 seconds. Now the idea is to find the velocity for this time. So what we can do is, we have the expression v equals u plus 80, and in this case, since we are looking at the y component, I can take this as uy minus gt. The reason minus gt is the projectile is coming down, right, during the total time of flight. So let us substitute and find the value of v. So v is equal to 80 minus 9.8 into 4.08, which we will get it as 40.016 meter per second. So this is the velocity. We can take this as the Vy component. Now initially if you see, we found Ux, or we can take this as, let's say, Vx, because we are looking at the magnitude of velocity. We got this as 80 root 3 meter per second, and now we have Vy, which is nothing but 40.016 meter per second. So the total velocity can be taken as root Vx square plus Vy square, which is nothing but root of 80 root 3 the whole square plus 40.016 the whole square. So this we can write it as 132.66 meter per second. So therefore the magnitude of velocity is 132.66 meter per second.